My name is Bartosz Witkowski. I'm going to start with you today this course, which is Introduction into Julia for Data Science. We are going to discuss today, firstly, the classical predictive models and the regression approach, what it is and how we do that in Julia. So firstly, we will start with a 20-25 minutes talk about how we understand regression, because some of you might have a totally different background, so that's mostly for that purpose. Afterwards, we will show you how to do that in Julia, and then in the afternoon, it's my colleague who is going to talk about predictions with the use of more machine learning type of forecast. Right. So firstly, what are the key differences between the two things that we'll be discussing today? So that's the classical econometrics versus machine learning. Well, first of all, why do we do econometrics? That's the key question. Well, we do that in order to answer two key questions. Question number one, you're interested in forecasting, in saying what value of this and that you can expect usually in the future. While on the other hand, that's about identifying certain relations. So you're trying to find why this and that is happening. You're trying to answer whether the fact that it's raining today is going to have some influence on the sales of ice creams, let's say. So these are the two things that we are interested in. So the question is, which type of tools is better for which purpose? And as usual, there's no single answer to that question because, well, generally, when you look at machine learning, the pros and cons, the main idea is to provide mostly the efficient forecasts of whatever you're interested. So usually that applies, for example, in credit scoring, when you want to say, is that guy going to pay back yes or no? So that basically works like a black box. You do not identify which factors have influence on what. You do not identify functions which link this and that. You just identify that in this and that case, for this and that pattern, you will expect this and that outcome. But you do not answer why. Well, since you are just identifying certain patterns, not really functions relating those objects that you have, you essentially need a lot of data for that. Because if you have small data sets, you will not be able to get sufficient information. So basically, all in all, the main advantage of machine learning is that it's much more accurate in forecasting of exactly what is going to happen than the classical econometrics, while on the other hand, it does not answer why something is happening. So that says you need more data for that. You also are not really able to identify what is going to happen if something really changes. So for example, suppose that the external conditions turn, that for example, we start having crises around the world. So your machine learning tools, which used to be very efficient in forecasting whether a person will pay back a loan or not, are not going to work that well anymore. While, on the other hand, the classical econometrics is quite different because we are mostly interested in identifying the data generating process, in identifying the relation between this and that, in identifying what the relation looks like. You can use these tools for forecasting, but generally, you will not be as efficient as with machine learning tools. So we basically build some functional relations, and we try to identify what exactly the influence of this and that is on the object of your interest. So since you are just identifying functions, and those could be, of course, multiple, in the simplest cases of the simplest functions, technically, you're not going to require many observations because theoretically, if you are just linking two variables with a linear function, theoretically, as I said, two observations would be enough to do that. Of course, that would not be good, but you could do that, while not really with machine learning tools. But all in all, you do not require such big data sets. So the pros of classical econometrics is that these allow you to identify the causal relations, to identify the determinants of this and that. And also, if something changes in the environment, these models are generally much more robust to the changes in the environment, or at least you can identify the influence of the changing environment. On the other hand, these are not going to be usually as accurate in forecasting, and also require you some knowledge or at least capability to guess correctly what is the underlying process, what the data generating process is about. So let's talk briefly about the main tool of the classical regression. So how do we do regression? Well, there's a couple of steps that you follow. Firstly, you identify what you want to identify, what you want to explain, and what you want to use as what the process defining the object of your interest really is. Well, that it says almost always, because sometimes you do not really know what the process is, so at least you need to make a guess or construct a model which is going to be some kind of compromise. For example, try to identify the influence, the relation between the value of the object today and its value yesterday or in some previous period. However, the next step, whatever happens, is that you need to propose the function that relates the object that you are trying to explain with some other variables, which are called independent variables or explanatory variables, which are supposed to have influence on the object of your interest. And then you need to gather a data set in order to identify the exact function that links the objects, that's the values of the dependent variable and the values of the independent variables. Well, there's one annoying thing about it. There's something called error term in it involved. Well, the thing is that when you build a function, it never or hardly ever is deterministic. So you cannot suppose that even if the value of the real estate depends on the size of the real estate of yours, that's the only factor, and the relation between this and that is always going to be the same. So essentially, there is some randomness in the process involved. We take care of that by involving something that's called the error term. Well, there's a couple of assumptions that you make about it. So let us see this. The easiest example ever, assume you want to, just as I said, explain the price of a real estate. Now, when you think about the data generating process, you might say, well, obviously, the key factor for the value of the real estate in certain places is going to be the size. So, of course, there are other factors too, but we are talking about the easiest example ever. So that's why let's limit the attention to just that. So let's assume that the link is linear. Of course, it might be any other function, but actually, when you think about this, probably in most countries of the world, it actually is linear. That if you double the size, you expect the price to be more or less doubled. If you triple the price, you expect the price to be more or less tripled. Of course, that's a statistic relation. So it's not like object per object case, right? So that's the thing. Well, as I said, of course, there might be many other functions. But again, easiest example, so we start with linear function. So if you link the price of the real estate with its size, the linear function will be something like that. You have two parameters in here, beta 0 and beta 1, and those are supposed to reflect the exact shape of this function. Now, this epsilon is the error term that I mentioned. This is to cater for the fact that if you take different objects, different real estates, it's not exactly the same function that's going to link the size and the price, because there are other factors involved as well, always, like, I don't know, location, sentiment, whatever. So that's the error term. What we do basically in econometrics is to assume that the expected value of that error term is 0, which means it's not 0 in each and every case. On average, sometimes the real price is going to be higher than you predict, sometimes lower, but the average will be around that. So the core question is, how do we get the beta 0 and beta 1? Because if you had those, and if you assumed that the epsilon has the 0 expected value, you could actually use this function to make a simple, not essentially very efficient, but still prediction of price. But most of all, you could answer what the influence of size on the price really is, which is something that my colleague was showing yesterday without even mentioning the name of regression. But that's actually the tool that he was using. So technically, you can think of that this way. Well, if you define y as price, x as size, your model is that. And if you assume that for one object, the epsilon is 0, actually, not that the expected value, but just the epsilon is 0, you could geometrically illustrate it this way. Suppose you have a sample of flats. For each of those real estates, you have information about the x and the y, so the size and the price. That's the x and y, and you can illustrate it in this two-dimensional set of coordinates with a single point. So then you get like a cloud of points, and since this, with the assumption that epsilon is 0, is nothing more than just a straight line equation, then geometrically, your problem is to draw a straight line in here through this cloud of points in such a way that this line would fit these points as well as possible. Now, what does that mean? That means, notice that if for a single x, you were supposed to predict y, given that this is your illustration, well, for this x, you would read the theoretical price of a flat. If this blue line was the illustration of your model, as go up, then go to the left somewhere in here. But you can see that the real price of this flat is actually this guy, y1. So the difference between your prediction and the true price for an object from your sample is the error that you are making. You can see it in here. For this object, that would be the value of the real flat price. That would be what your model is predicting. So this length is called residual, and that's actually the mistake that you're making. So that means you would like to draw this blue line as close to these points in the vertical term. So you'd like these vertical lines connecting these red dots with this blue line to be as short as possible. The question is, how many objects do you need in your sample to do this? Well, theoretically, 2 is enough. But notice that, well, because with 2 points, you can draw a straight line. However, your model will be very poor, because if there was any change in y or x for one of these 2 objects, that would not really work well. So obviously, the more the better, but you do not need lots of those really, as you do in the case of machine learning. All right, so what's the basic interpretation of what we got? If you suppose that this is the equation of the line that you saw in the previous slide, I would say if the price is given in the thousands of US dollars, the surface is given in supposedly square meters, then that would suggest that an additional square meter would, on average, increase the price by approximately 7,000 US dollars. That's the outcome of your model. So basically, looking at the estimate of this parameter, you could guess or draw some conclusions about the relation, the link between surface and the price of your flat. Of course, that does not mean that for each and every flat that would work exactly like that. That if you take 2 flats, one of them being 60 square meters, another 61 square meters, the difference is always going to be 7,000 US dollars. Why? Oh, firstly, because these are just the values of parameters found in certain sample. So that says they are subject to a statistical error. Secondly, because we assumed here that the value of the error term is just equal to its expected value, that's the 0. However, in real life, it's there. So there are going to be some inaccuracies. So you have to remember that that's just a statistical relation. However, it exists. Now, there's a measure, well, a number of measures, I should say, huge number of measures that are supposed to show us how good your model is. The simplest ever is probably the R-squared, so-called coefficient of determination. This guy works that way. Now, this case that you can see on the left-hand side is a situation in which the cloud of points from your sample lies very close to this line that is the illustration of your model, while on the right-hand side, it's just the opposite. So clearly, in the left case, the model fits the data much better than on the right-hand side. Now, what's happening here probably is that on the left-hand side, you can see the situation in which really the price of the flat depends on its surface, and your model fits that pretty well. While on the other hand, on the right-hand side, you have a situation in which there's an uncoordinated cloud of points, and clearly there's actually no relation between the surface and the price. So trying to build your model is actually not really a good idea in here, because there is no link between these 2 functions. Or there are some other factors which you forgot, or for any other reason did not include on the right-hand side. If you had done it, your model, instead of being a 2-dimensional case with x and y, would become a multi-dimensional case. And then you would not be able to illustrate it, obviously, in a 2-dimensional set of coordinates, but still it would be there. And possibly, for example, for these flats which are here on the top with the higher prices, maybe there's something else that influences the prices other than the surface. All right, as I said, one of the most annoying parts of the story is that we have this error terms. We have also numerous assumptions that we make. Now, first of all, let's start with the generalization. As I said, if you had just one variable of interest, that's the surface of the flat that influences the price, your story would be the model with one regressor on the right-hand side, with one variable, single x. However, usually we have many of those, so that constructs a model with many x's. If we assume linearity, that's the way it looks. Why don't we see it geometrically? Oh, because you cannot illustrate it in a single string with a 2-dimensional plot. You could do it with some k-dimensional plot, but come on, it's like you cannot see it in the screen during a short presentation. Now, is that really useful? An example is an old example, but that's for a reason. An example comes from Professor Altman, Edward Altman, who works at Columbia University. And Professor Altman, that's him in the slide. Professor Altman in 1968 was probably the first person to construct an index which was supposed to show what is the risk involved in renting money renting money to a company. He published an article, which you can see in here in the Journal of Finance, in which he proposed the following model, with Z being the overall index of the risk of the default of a company, and a couple of financial measures being involved in here. You do not see it very clearly, like the print is not very nice, but that's because it's a scan from the journal itself directly. So there's like pre-digital era. As you can see, there are 5 axes on the right-hand side, all of them being certain financial indicators, and each of them has some parameter. So it's like an estimate of some beta, 1, 2, and so on in front. This is to reflect the influence of the particular financial measures on the total measure of risk involved in lending money to a given company. You might say, all right, so how much data did Altman use to estimate this, to construct this model? And that's an interesting question. Possibly you've heard of that. If not, then this might be surprising. He had the data set of 66 enterprises. So 66 is like nearly nothing. Some would say he was lucky. Some would say he was a very good professor. Well, definitely, I'm in favor of the second option. However, this shows you one thing. You can do econometrics, the classical econometrics, with even few observations. Of course, year by year, there was like, there are many people nowadays saying, well, the Altman's measure is not perfect because of this and that. And they're obviously right, but come on, that was 50 years ago. So since that time, a number of things have changed, and we have had a lot of opportunities to simply improve on this measure in case you wanted to. But this shows the application of a very simple econometric model proposed by Altman to measure the risk of default of a company. How do we get those parameters? That's a core question. Well, there's a number of ways, but the most frequent method in the case of linear models, is called ordinary least squares. So how does that work? When you recall the slide in which I showed those vertical lines, which I said should be as short as possible, because that would mean those residuals, the distances between the true value of the dependent variable and what your model says, should be as short as possible. Now, the so-called ordinary least squares consists in minimizing the sum of those residuals, that's those distances, squared. Why squared? Oh, because otherwise you would have sometimes the negative error, sometimes the positive error, and those would sort of wipe out one another. So if you take them squared, in whatever direction you make a mistake, those do not wipe out one another, right? So that's one of the reasons. Technically, you could use the absolute value as well, but you do not do it for 2 reasons. One is a mathematical reason. The second is you would like to impose higher penalties for big errors. So if you take squares, if you make a big mistake, well, that's like higher penalty for that, and that's your target. So how does that work? Well, as I said, one thing that we need to understand is that there's a big difference between values of parameters and the estimates of parameters. The values of parameters is something that we would like to have, but generally will never have. You might get the values of those beta 0, beta 1, and so on in a given sample. But come on, that's just a sample that you're using to, well, get some approximate values for a given case. If you want to generalize that for the whole population, you can only think statistically and say, what I got in the sample is my estimate of what's happening in the whole population. And that's the key difference between calculation and estimation. You can calculate a value of certain function, but in case of parameters, if you want to think of those as population parameters, you only estimate those. And of course, you base your estimation on the values of parameters calculated in certain sample. And the ordinary least squares allows you to get those parameters in the sample, which you should think of as the estimates of parameters in the population from which your objects come. So those ordinary squares approach consists in minimizing the sum of squared residuals, the sum of squared distances between the true and theoretical values of the dependent variables. That's the idea, as you can see in the slide, and there's a bunch of assumptions that we need to make for that to work. Actually, here are those assumptions, and it takes quite some time to cover that, but as you can see, one of those we actually already mentioned, that the expected value of errors are zeros. Well, some of them are technical, like the x's are not collinear. Well, if they were collinear, that would mean you have two variables that truly represent the same thing, so you do not need them. But there are two which are not that obvious, namely one, the last one, that's about the variance of the errors, which should be constant for all the observations, and the errors not being correlated with one another. So that's like, you could think of that as saying the distribution of error is the same for each and every observation and does not depend on anything else. So it means if you took two real estates and if you wanted to base your estimates on your function on many objects, including these two real estates, it's not that one of them is more important than the other because the variance of the error term is lower or higher. It's not that they are somehow linked with one another. No. Now, the first assumption is a particularly problematic one, that the x's, the independent variables, so in our case, that was the surface of the flat, are not correlated with the error term. There are two reasons, main reasons for which this can be violated. One of those being so-called omitted variable bias. And this is something that my colleague is going to show you in a few minutes with an example why this assumption is so important and what happens if this is violated. He will show that to you with simulated data, because you could do this analytically, but that's a bit of hassle. So we shall see how to use Julia in order to show it. Now, if we assume that those assumptions are fulfilled, you can show that this would be the form of the function that you should use to estimate the parameters beta1 and beta0 in the case of a model with just a single regressor. Now, this is, as I said, only works if you have one x. That's the example with the value of the flat depending on its surface. However, in real life, usually you have a number of variables on the right-hand side, just like Altman did. So that's what you need to do. That's the vector of parameter estimates based on the ordinary squares method. As you can see, there's, for example, an inverse of a matrix in here. Now, this inverse of a matrix is why you cannot have collinear x's, because if your x's were collinear, there would be no inverse of this x transposed x matrix. It would be just a singular matrix, so that's why. And this is the way you would need to write down the X matrix. You could write the formula in the matrix notation. You could write it down in scalar notation, whatever you prefer. But still, as you can see, this formula is just based on the values of X's. That's the independent variable, and Y, that's the dependent variable in your sample. So having this formula, you can estimate the values of parameters of linear regression and then interpret those, as you could see. Now, how do we know that the formula looks this or that way? Well, we use calculus for that. So as I said, we minimize the sum of squared residuals. And you can then say, oh, what's a residual? That's the distance between the true value of y and what your model says. Now, what's the thing that your model says? Well, your model says that the theoretical value of y should be x multiplied by the estimate of the parameter plus the estimate of beta 0. So that's what your model says. So now take what your model says, subtract it from the true values of y, take these distances or differences actually squared, sum those up, and minimize with respect to beta. And here you go. When you do that, that's the formula that you do. So obviously, due to the lack of time, we are not going to show the derivation of this formula, but my colleague is going to use the module that applies this technically. All right, if that works, we have so-called Gauss-Markov theorem, which says what are the properties of the OLS estimator. So what can you say about statistical properties of the results that we got? So again, recall what we get is the estimator. That's a function of your data set, function of your data, and the value of this estimator in certain sample that you have. So among the real estates that you took to guess the value of betas are the estimates, the numbers that you obtain. So while in reality, what links the y and the x's are the betas, what you get are the values of beta hats in a single sample. Now, what can we say about these beta hats? Well, there is an acronym, which is a very nice one, which says if all those assumptions are fulfilled, then this beta hat, the OLS estimator, is blue, which abbreviates best linear unbiased estimator. So that says actually 4 things. One of them is that it's linear, which is something that you can see, that obviously it's a linear function of y, so nothing to talk about. But what's best, what's unbiased? Well, unbiased means the expected value of your estimator equals the true value of the parameters. So it does not say that in each and every case, if the true value of parameter is 5, then your guess obtained with the estimator is going to be 5. It just says on average, you're going to be there as long as your assumptions hold. Now, there is another property, which is consistency, which is a bit less intuitive, that basically says if you keep increasing your sample size towards infinity, the probability that the distance between the value of your estimator and the true vector of parameters shall exceed certain very small gamma is tending towards 0, right? So that basically says the bigger your sample is, if you keep increasing your sample size, your values of estimator are going to head towards the true values of parameters with the decreasing towards 0 variance as well. So that's more or less what it says. And finally, what is that best? Well, this is the property of efficiency. It says there is no other unbiased linear estimator which would have lower standard error than your estimator. Now, what's the standard error, you might say? Well, the standard error is basically by how much are you mistaken when you calculate the betas, because recall that these are just estimator. So the true values are not essentially what you get. Well, you might be guessing closely or not closely. So the error shows on average by how much you are mistaken. Now, these errors have a very big and important meaning because we use them often to draw conclusions regarding significance of the regressors. Now, what does that mean? Suppose that technically you build this kind of a model. You explain price of a flat as a function of size, but also age of the owner. Does that make sense? Not at all. But still, can you do this? Well, of course you can, as long as you have the data. So suppose you did that. Now, then you got some numbers. You obtained the estimates of beta 0, beta 1, and beta 2. Recall the estimates. So suppose that the estimate of beta 2 is some number, say 0.2. Now, what should be the beta 2? If the age has no meaning, the beta 2 should be 0. However, it's just the estimate. It is not exact number because of the error. So that says, well, if I get some estimate, how can I know if it's non-zero whether it's just the statistical error that makes this beta 2 a non-zero, or indeed the influence of age exists, but it's very small. That's why the beta 2 is non-zero, but very close to 0. Well, as I said, that's the difference between beta 2 and beta 2 hat. If we knew the true beta 2, there would be nothing to talk about, but we just have the estimate. So the true value of beta 2 does not essentially mean that the estimate of beta 2 is going to be 0 as well. We use the estimate of beta 2 to perform tests of significance. That is one of the statistical tests. So just like in every statistical test, we formulate 2 hypotheses, the so-called null hypothesis and so-called alternative hypothesis. Under the null, we say the given variable has no meaning, is not statistically significant in the model, while under the alternative, it's just the opposite. So under the null, we say the parameter is 0. Under the alternative, it's just the opposite. Now, we can show statistically, and that's what we are not going to derive, but my colleague is going to show you with the generated data, that this function, the beta 2 hat divided by the standard error, follows the t-distribution with this number of degrees of freedom. And you actually might recall that this is nothing more than the z-score, which my colleague also used yesterday. And the difference between this guy and the z-score, as you saw it yesterday, is that in the z-score, you would subtract the mean as well. But notice that under null hypothesis, the mean is 0, because we know that the estimator is unbiased. So that's actually a z-score. All right, then. So basically, this should be close to 0 if the null hypothesis is true. The question is, what's close to 0? Well, if the null hypothesis is true, these are the t-distributions with different number of degrees of freedom, different n minus k plus 1, where n is the sample size, k is the number of regressors. Now, that means they have the expected value somewhere here and the mode as well, around 0. So if the null hypothesis is true and this is the distribution of this test statistic, you should get the value of this test statistic somewhere around 0. But what's around 0? If I get the value of minus 0.5, is that around 0 or is that far from 0? If I get it to be 5, is that around 0? Well, the answer is, firstly, this is only going to work if the error term is distributed normally, but we have central limit theorem. So if our sample is sufficiently large, which does not require very many observations, we can do it as. Now, what's very close to 0? You will see that Julia provides, just like other software, so-called p-values. Now, how does that work? Suppose that your value of the t statistic for certain variable in certain model is some t star. Now, in the ideal case, you would get the value of the test statistic to be exactly equal to its expected value, but that's not essentially what you are going to get. You would get it in the long run if you just perform a number of experiments, not exactly in a single case. So if you get it to be somewhere like t star, the question is, how probable is it that under the null hypothesis, when the test statistic is distributed t, would you get the t star as far from the expected value or even further than you just got? So that's actually asking, how improbable is it, or on the other hand, how probable is it that under the null hypothesis, you would get the value of t statistic which is not equal to the expected value, but differs from the expected value in the true distribution by what you got or more? The answer to that question is so-called p-value. So actually, you can see that if the p-value equals, for example, 0.1, that means, now, what is the probability that your value of test statistic under the null hypothesis would differ from the expected value by what you got or even more? Well, that probability is 0.1. 0.1 is not so much. So you might say, okay, if the null hypothesis was true, such a situation would not really happen frequently. So maybe the null hypothesis is just false. Well, if on the other hand, your p-value was 0.7, that would say in 0.7, so that's 70% of the cases, your value of test statistic under the true null hypothesis would differ from 0 by what you got or even more. So does that mean that the null hypothesis is false? Probably no, because that's a typical case. So you see, when the p-value is very low, like very close to 0, that says probably null hypothesis is false. If it's very high, like getting towards 1, the higher it is, the more likely it is that the null hypothesis is actually not false. So we'll be tending to reject the null hypothesis, in this case, meaning finding the variable to be significant if your p-value is close to 0. How close to 0? Or, well, if it's 0.05, what does that say? If it's 0.05, that means 5%. That means if you reject the null hypothesis, if you claim that the variable is significant, there is a 5% chance that you are actually wrong if your p-value is 0.05. Because that means in 5% of the cases with the t statistic which you got, actually the null hypothesis will be correct. So in this 5% of the cases, you would be rejecting the true null hypothesis. That's a kind of error that you're making. So actually, the lower the p-value is, the more certain you are that you should reject the null hypothesis, with its value being equal to the error consisting in rejecting the true null hypothesis. All right, then. So this is going to be it. Regarding this short introduction, of course, there's a number of other issues, such as you might say the regression is not essentially always linear. You might say, well, what kind of data do we have in order to estimate these models? Well, there are different types. You might get the data across objects over time, across objects and over time. So there are different types of models that you construct. There are some assumptions which I mentioned. Maybe we should validate them, but there are also many other assumptions, many other properties of the model that we should test for. There are different ways of estimating parameters if these assumptions do not hold. Finally, there's a question, if you find a variable to be significant, does that mean that there is causality? Does that mean that X influences Y? Or maybe these are just covariants. They are changing parallelly because of this and that reason. There's like huge research by guys who got a Nobel Prize in 2021, And actually, the issue of causality has been within the scope of series econometrics over many, many years, because, well, covariation is not essentially causality, which many people are misled by. So, these are the basic things. Well, whether our regression is spurious or really there's causality. These are the main things that you should think of, and there are many, many others. But that's like, short introduction so that Mateusz could show you how to do this in Julia now.
Cool, thanks. So thank you, Bartek, for this nice introduction to the basics of econometrics or linear regression. At this second part of mine, I will go through Julia notebook that I have prepared and demonstrate some of the statistical properties that Bartek has introduced. So we will be working in this part. I will be aiming to finish at 12:30, but if like 10 or 15 minutes, it will be prolonged. Sorry for that. So the folder on the GitHub repository is day 2A, which is classical predictive models. 2B will be for the second part of the day. At this folder, there is both Bartek's presentation that he presented, so you can download those PowerPoint slides, and also the Jupyter notebook we are going right now to go through. So, as it was yesterday, you need to go through some steps to and preferably to run the Jupyter notebook using, for example, this snippet code. So like running after making the copy of repository and running Julia, you probably need to preferably run this snippet code, and then the Jupyter notebook will be opened. And by going to the folder for the second day, you can click on the notebook called Classical Models. So this is where I am right now. Agenda for this notebook is following. So we will start with generating artificial simulated data set. We could, potentially run a linear regression, of course, on real data, but the nice, property of running simulation is that we will be able to demonstrate some systematical statistical properties which couldn't be done easily on the real data, because on the real data you have just one single like a drawing of data, and having simulated process, you can have multiple data sets, so you can estimate your regression on all of those multiplications and come to some conclusions. So I will discuss exactly in a sec what this data is. Then we are going to visualize this data and run a single estimation of least squares on a single data set. We will get results including coefficients, standard errors, p-values, and r-squared that we are going to interpret. And then we will repeat this estimation step 100,000 times, which is called so-called Monte Carlo simulations, and we will be able to demonstrate those statistical properties called unbiasedness, and also it will be easier for you to interpret the linear regression results having seen these simulations. And also, at the end, we will introduce some kind of problem, which is called omitted variable problem, and we will see what are the consequences on the estimations given this kind of omitted variable problem. So let's start with running following cells. The second cell actually is loading essential packages that we need for today. You should have them loaded if you followed the instructions from the very beginning. If not, you might want to uncomment the second line in the first cell where you are adding those packages which might be missing, and then the second cell should be working normally. So it's working on my side. Then the third cell is about setting up the seed. Since we are going to simulate pseudo-random numbers, we might want to guarantee the replication of those results, so all of us have the same results. In order to do that, we need to align on a common seed, which is 1 in this case, but it can be whatever number you wish, but to be the same on our computers. So yeah, I encourage to set it on the same values, but if you don't, some detailed results will be a little bit different, but statistical takeaways will be the same. So now let's go through a description of data set. Exactly what I mean is data generating process. This is how we call in common econometrics the mechanism behind which data is generated. So you can imagine we are maybe a store manager, or we are providing some consulting services to the store managers about how to set up optimal prices. And this regional convenience store sells some products, and here we are interested in bottled still water. And here we will have 4 types of information: weekly based data about the temperature in this region, also average of the rainfall, the price in a particular week and the store, and demand, which is simply the sales volume of the bottled still water. And those 4 variables are somehow related. So first, starting with the temperature, is actually the only variable which is independent, not dependent on other, as you can see. And this is generated as following. We are taking like 10 plus 5 multiplied by random variable drawn from standard normal distribution, as you can see here below. So I'm assuming here's Celsius degrees, okay? Then the second variable is the rainfall, and this is dependent on temperature. It's kind of like non-linear function, max function, dependent on the temperature. We will see soon visualizations of this data, but this is how rainfall is related to temperature. And then the price is one of the most important here information. This is how the historical price was set. And we see that this store manager was setting price in relation to temperature. So the higher temperature, the higher the price. Was the logic behind price setting here. And you can imagine that, in real world, if the temperature goes up, drinks, beverages are needed, and business is accommodating that and usually setting prices higher. So this is a smart strategy. And finally, what will be our target variable or our dependent variable is demand, so the volume sales. And this will be dependent on both price. Of course, economists assumes it's negative.
Can you increase the...
Yes. Is it enough or more? Okay, no problem. Thank you for letting me know. Yeah, so the last equation is demand dependent on both price and temperature. Here, I do not specify beta's values. They will be soon specified here as a default parameters values. But yeah, economists assume that demand curve is downward function, negative. So the higher price, the lower sales level. So this is how we should typically expect. While the temperature, of course, should have positive impact. Yeah, so the higher temperature, the higher sales of still water. And this is how, we are here defining the Julia function called DGP, standing for data generating process, with following arguments, having default values that we will not going to change, but you can experiment with other values. So the first argument is n, standing for number of data set observations. So here you can think as a number of weeks. Beta 0 is intercept, sometimes called bias in the deep learning literature. And finally, we have those two coefficients, beta 1 equals to -1. This is the impact of price on demand, and beta 2 equals to 0.25, measures the impact of temperature on demand. So having those arguments defined, we are then having those equations actually, written in Julia. So we have, both defining temperature, rainfall, price, and demand. What might be interesting and was discussed yesterday is this point-wise calculations. Yes, because this is a vector and this is a scalar, and in algebra you cannot simply add scalar to the vector. You need to do a point-wise operation here, or so-called broadcasting, and this is why we have those point. The same applies, the same construction, the same role is played by dot here and somewhere else. So this is how we define those variables, and then we are returning the data frame. So I'm running this function, and then we have a single data set being generated. As you can see, it has 100 rows, 4 columns, and these are the examples. Yeah, so a lot of numbers, but let's take a look on graphs. So first is histogram demonstrating how the temperature is distributed. Since temperature was independent, exogenous, it's not related, it's not dependent on anything. It looks like this. Then let's take a look on some relationships on the scatter plot. So here we have two scatter plots. What is nice in Julia, you can using one comment, you can output 2 scatter plots, or even 3 or more, as you will see soon, using one comment. Yeah, so we are just simply entering here a matrix instead of one series, one vector. We have the matrix of the price column and rainfall column. So the output is this nice 2 scatter plots. So first scatter plot is demonstrating relationship between price and temperature. As you can see, is positive. And this is exactly what we have assumed, that the store manager is setting prices higher, the higher the temperature. Yeah, so it is confirmed by this scatter plot. Also, at the next cell, you see the correlation being computed using core function. And you can see that this correlation between price and temperature is quite strong, of 0.72. Yeah, so correlation is between -1 and +1. So 72 is quite a lot. And we see nicely a strong linear relationship. Then rainfall depends in a non-linear manner on temperature. This is this max function being applied here. So you can see that negative temperatures corresponds to 0 rainfall, and it's like ReLU function in deep learning. Yeah, it's like max function, so it's very similar.
Leaky ReLU, actually.
Excuse me.
It looks like leaky ReLU.
Yeah, it might be. Sorry, we have some technical problems.
Yeah, but you know what to do with it or not? No.
Tak.
So what I meant by ReLU and leaky ReLU, maybe while we are waiting for those of you. So standard ReLU function is like this. Actually, it's the origin 0. So you have a key, you have 0, right? And you know, it's a well-known function, and nice. The problem is that it's not differentiable. It's at 0, which means that in some applications where you need full differentiability of the function you optimize, it's a problem. So leaky ReLU is a function that has almost the same shape, but it's designed to be differentiable everywhere. So like removing this king. So when I looked at this plot, it looked like more like, you know, smooth transition rather than a king. So that's that's the reason for my comment.
Yeah, thank you for that. But
although what's snowfall considered rainfall or no? That would also explain the 0.
Sorry.
Was snowfall considered rainfall?
sorry.
If it was snowing, was it considered as raining?
Okay, so you know, this is just assumption, yeah. So I'm not having snow in my model, yeah. You can think. So this is what is nice about, you know, simulating and assuming whatever you want, yeah. And then having this knowledge of what the true value are, you can then compare estimates with actual true value, yeah. So in real world, you don't know what true value are, as Bartek said, yeah. But here we are in charge here and able to know what is correct and not. Okay, so this was the impact of temperature on both price and rainfall. The next set of scatter plots, 3 of them, are 3 features: price, temperature, and rainfall impacting demand. And also at the bottom, we have Pearson correlation similarly calculated. So starting with the first left-hand graph, we see the scatter plot of demand versus price. It's quite cloudish, like not any like relationship obvious here. From economics, we should expect negative relationship, but actually the correlation being calculated is positive. So it might be confusing, yeah, firstly, and we'll see later why is it so. So this is the first you know, graph. Then we have demand versus temperature, and here we see, you know, obvious positive relationship, which is also confirmed with the strong correlation of 55. And this is intuitive, yeah. We should expect this one. And finally, demand versus rainfall, we see some positive relationship. Correlation also confirm it partially with like 24, which might be a little bit strange because in our equation, rainfall was not impacting anything. Yeah, so in the demand equation, it was only price and temperature which was impacting demand, not rainfall. But we see still this relationship because rainfall is related to temperature and temperature impacts demand. So this is the reason why we see this effect. Okay, so now let's start do actual estimation. And the first cell is using algebra manipulations according to the formula provided on the slide by Bartek. In Julia, additionally, it's quite nicely written and easily. So I'm defining here this least squares function and then applying to our data set, and the result are the 4 estimates for 4 coefficients, beta 0, 1, 2, and 3. Yeah. We will soon interpret those, but maybe do the same using GLM package, which stands for Generalized Linear Models, very similar to R programming language. So take a look on those, because in real life you will be rather leveraging this GLM packet rather than using on your own algebra calculations. So using this package, in the first step, you are defining the specification of the model. So using this formula statement, you are specifying what is the target variable or dependent variable. This is a demand in our case. And later you are defining features or exploratory variables or independent variables. As you can see, many names for the same concept. Yes, please.
Yeah, so you know, it occurred to the following comment occurred to me. So you kind of have here a choice. So either you use this low-level API that Mateusz showed above, which is not super convenient because it's low level, but the benefit is that it's has 0 overhead. So actually, if you, for example, need to run 1 billion regressions, this is the fastest way to do it. On the other hand, if you need to run 1 regression and you want your code to be readable, so you'll be able to use variable names and not create manually the matrices, then you can do this. And of course, under the hood, the package will do everything for you. But you need to remember that there is a trade-off, that if you don't do it yourself and package does this, it means that there will be some performance overhead. So in case of other languages, probably it's not that relevant, but in case of Julia, it is kind of relevant because often people use Julia to have very fast execution speeds. So actually in Julia, indeed, there is a choice. So sometimes you might opt in to use this low-level interface if you really are doing a lot of simulations and need to run them very fast.
Thank you, Bogumil, for that comment. Indeed. Good. So we have this model being specified as followed. We know as a data creator, data process creator, that price and temperature are the correct drivers, yeah, the correct variables, while rainfall is not necessary, yeah, but still we are keeping it here. So having the specification being defined and having our data set generated, we can apply least squares estimation using this LM linear model function and saving results to the fitted OLS variable. And we have this nice output, but yeah, I make it, yeah, maybe this. Okay, it will be better, yeah? So what we see here, we have 4 rows corresponding to 3 variables and 1 intercept. So those 4 parameters we have estimated here. And yeah, the first column are the coefficients estimates. So these 4 values, 29 and so on, are exactly the same, should be exactly the same as this vector, yeah? It looks like the same, yeah? So, and since we know the true values, we can compare and evaluate this estimator. So the true intercept was actually 30. You might not remember, but if we come back to the DGP, it was here beta 0 was 30, yeah? So it is a true value. So this is something we should expect our estimator to output. It's 29, quite good, I would say, yeah, quite close to the 30. And then we have price impact. It should be -1, we have minus 0.94, also quite well, I would say, quite close. Then temperature, it should be 0.25. Again, I would say 27 is a good guesstimation. And rainfall, what should be the value here, the true value? 0, yeah. And we have actually also quite near close estimate, yeah. But we know the true values, yeah. So we can say, okay, this OLS as Bartek presented is indeed blue. It's really best. It's really good, yeah. But in real world, we will not know the true values. So we need additional columns here, which will tell us, how good these estimates are. So this is the standard error that Bartek has described to you. And yeah, those standard errors measures, the precision of those estimates we have just go through. So as you can see, this estimator is like not sure whether it is 29 or maybe 30, 31, but it states, expect error of 3.2, yeah. And also we can see something which is related to that, which is confidence interval. So having this actually interval, not a point estimate, but the interval stating that with high probability of 95%, a true value, which you do not know when working on the real data, this true value will be within this confidence interval. So we can see, that this confidence interval is, quite. It's not very narrow, but not also very wide. Yeah, so it's a good value. On the other hand, when you see a rainfall, you see this confidence value consisting 0 inside. Yeah, so this interval, confidence interval, is from minus 0.1 to plus 0.03. So this interval consists 0 in between. So this estimator is, not sure whether the actual true value is actually maybe 0. Yeah. So therefore, also, it is consistent with this p-value we have here, which is statistics we use to make a decision about when we do hypothesis testing, and we test whether this rainfall is significantly impacting demand. And we see that since this p-value is, higher than either 5% or 10%, depending on your threshold you choose, we see that we cannot reject null hypothesis stating that there is some impact. So we cannot state there is some impact. So we are like taking this null hypothesis as our kind of decision and stating that there is no impact. Yeah, of course, in reality there might be, yeah, but this is statistical inference. So yeah, but with correspondence to the correct drivers, correct features, price and temperature, we see that they are, statistically significant with very low p-values. And also this standard errors are also quite, relatively low. So also confidence intervals are also relatively narrow. So these are the typical results you will get. Also, you can calculate in Julia R-square, which is here 41. So, it's normalized metrics from 0 to 1. So 41 is in the middle, yeah. And the interpretation is, that 41% of the demand variance is explained by the variance of our predictors. So we are able to, explain using this model nearly 42% of the variance of the demand. Yeah, and variance is what we want to explain. Okay, good. So this was a single estimation on a single data set. And you might wonder, how such estimation would perform on maybe different data set, but generated from the same process. So have we had a lag? We got some quite good results, as you have seen. Yeah, those coefficients have been quite close to the true values. So have we been lucky? Or maybe it's something systematic we should expect. So therefore, we are going to run Monte Carlo simulations. So we are going to repeat the process you have seen here quite a lot of a number of times, to be specific, 100,000 times. So we are going to save each time for each simulations this kind of informations. So here we are creating an empty data frame composed of 6 columns, and for now there is no rows. And we will populate this data frame with rows in simulation. What are the columns? So we want to save all coefficients estimates from beta 0 to beta 3, but also beta 3 p-value. What is it? This is this value. So we don't want to have all 4 p-values, but only p-value for the rainfall. So what we want here is just like this, to have p-value higher than 10% or 5%, because if this happens, we know that hypothesis test provides us with a good decision, yeah, that we are aware of. So we will see if he is correct all the time, or maybe, or how often, yeah. And also we are saving r squared to see how it is differ. Okay, so let's run the simulations. This is a for loop. As Bogumił said yesterday, for loops are fast in Julia. We can, use it quite efficiently. What we are doing in this for loop, the same what we did just a few moments ago. We are generating data set from this DGP process. We are fitting our linear regression, and we are adding to our data frame coefficient estimates and this p-value and r square. And this is what we get. We get, columns, we get data frame. So take a look, maybe on this beta 0, we expect 30. And we see different values, 27, 29, 30 something, 34. So we see, most of them are quite near to 30. Also for beta 1, we expect -1. Again, we see a lot of random values, but around -1, plus minus something, yeah. And the similar we see for other columns. But maybe let's take a look on the p-values. Here we would expect p-values needs to be from 0 to 1, and here we expect preferably p-values to be above 10 or 5%. It would mean that significance testing is correct. And here I can see we see everywhere above 10%, which would be great. Yeah, so in all those rows, in all those simulations, statistical testing was correct, which is amazing. We will see if it is something regular. So right now, since we have 100,000 observations, it's easier to visualize it using histograms, for example. So here we are visualizing the histogram of this beta 0 intercept. And of course, we see, that the average is 30, yeah, more or less. And it has some, deviation. So typically, the estimates, it's not lower than 20 and not higher than 40. Yeah, this is what we see. And what is the takeaway of this? You can think of this intercept estimated by least squares at the value of 28.5. So this is a single estimation. To be precise, so this is the last one, okay? you can think of each of those estimates as a random variable being drawn from so-called sampling distribution that we have just approximated using Monte Carlo simulations. So yeah, so each of the estimates you get, you can think is a random variable from this distribution. And you can expect that, you know, on average, you will be correct. Yeah, because the expected value of this distribution is exactly 30, which is equal to the true value. So this is called the unbiasedness property that Bartek was mentioning. Second thing is this standard deviation of this sampling distribution, and it was also estimated. So the standard error is estimate of the standard deviation of the sampling distribution, but itself it is estimate, so it is also you know, have its own error. So you know, 3.24 is the estimate, and using Monte Carlo we have a better estimate of that, which is this value. So so you see it's also quite close to each other. Yeah. So you should think of those standard errors as a standard deviation of such sampling distribution standard deviation. Yeah. And finally, you know, we can also using Monte Carlo, we can more accurately calculate confidence intervals, which are also estimated by least squares having here. Yeah, so this is the estimate of confidence interval, and using Monte Carlo, we have a better, you know, estimate, which is quite close to the true confidence interval. In this one. Okay, so let's you know, we can now move to the remaining coefficients. So we can see, for example, beta 0 sampling distribution. We know the true value is -1, and indeed this sampling distribution has the expected value of -1. It's centered around -1. So this demonstrates the unbiasedness property. But still we see some not so small standard deviation. Yeah, that the actual estimate might be even minus 0.5 or minus 1.5. But you know, but still not rather like 0 or positive values are rather not possible. Yeah, to take place here. And also we have, you know, sampling distribution for temperature. The true value is 0.25, and we see it's centered around 1/4 with some smaller standard deviation than the price. And finally, we have this rainfall, which we know is not significant. Its coefficient is actually equal to 0, and also this sampling distribution is centered around 0, but still having some deviation. Yeah, so you will never get, you know, 0 as a coefficient for not significant variables, but some random variable which is around 0. Yeah, so and this is how it works. And yeah, and I have outputted some, you know, takeaway. They are similar for all variables, so you can and they are quite similar also to what we have already go through with correspondence to the intercept. So I will skip that, but feel free to go. And to better understand it. What I want to show now is another sampling distribution, but this time not of a single coefficient, but rather of p-values for this rainfall. So right now we are seeing, I'm referring right now to this number, as you might remember. So in our single data set, it was 0.25. So we could conclude that rainfall is not significant, which is correct. Also here we have seen this p-value also above 1/10. So also all those examples provided us with the correct decision regarding the significance of rainfall impact on demand. But here we see that those p-value are like evenly distributed across interval from 0 to 1. It's uniform distribution actually, yeah, with some small randomness. And this is what you should expect when you are calculating p-values for like here for variable which is not significant, for a test in which null hypothesis is correct. You should expect the uniform distribution as we have here. What does it mean? It means that if we take, a 10% threshold as our significance level, we should expect to make errors in 10% cases. So you see that, here we have 10% simulation results, which resulted in rejecting null hypothesis, stating that there is no impact of rainfall on demand. So we concluded that there is impact of rainfall on demand, which we know it's not correct. So in 10% cases, we would make error, which is something you should expect whenever you are doing statistical testing, that there is some error. There are two types of error. First type is controlled fully by you when setting this significance level, threshold level, either 5% or 10 or maybe something else. But there is also another type 2 error. And this is something I'm, discussing briefly in these comments. So I don't want to go right now into details, but encourage you to read on your own later if you are interested. And the similar, exercise we are doing for R-square. So also something we are not going into much detail. What I want to do instead is to do similar Monte Carlo simulations, but this time assuming a wrong, not correct specification of the model. So this is a Julia code where I'm defining, a very simple, not multiple regression, but simple regression with just one feature, which is price driving demand. So we are here omitting temperature, which we know has impact on demand. We are also omitting rainfall, but this is actually a good thing because we know that rainfall is actually not significant. But having missing temperature might result in some problems. We will see soon, okay? So let's start with, as previously, with just one estimation. And what we get? We get estimate of measuring the impact of price on demand to be positive. For economists, it's something, not typical. Yeah, so it would mean that the higher price, the more demand, which is, not intuitive and nothing to be expected. Yeah, so this is suspicious. The question is whether we have a bad luck or maybe it is systematic. So therefore, we are going to run Monte Carlo simulations. But even based on those results, you can interfere already whether this is systematic or not. So having this, standard error being relatively quite high to coefficient, it's more than 50% of the coefficients itself. It results also in those t statistics. So it's high, but also not very low. Yeah, so it's somehow resulting in p-value being 6%. So depending on the significance level, you would say either that price has impact, but positive impact, which is quite the worst case, I would say. So it would be better to say price doesn't have impact on demand. For economists, it's better statement than stating that it has positive impact. Yeah. So you see, it is you see some systematic wrongness, systematic problem here. Yeah, because if it would say, I mean, either way, it's not negative. We should expect negative impact. Yeah, and there is no chance there would be, as you can see here, even. Okay, there is a very low chance it might be negative because confidence interval, the left bracket is negative. But even if it is negative in business sense, like in interpretation, it's very small. So sometimes we distinguish statistical significance from business significance. So even if it is statistical significant, it might be like the magnitude of the impact. It's not important for the interpretations, and this would be the case. Yeah. So even if it would be negative, still, it's not enough. So yeah, let's also run these Monte Carlo simulations in the same way as we did before, but this time having a wrong specification. And as you can see here, we have some beta 0. We know the true value is -1, but what we get mainly positive values. We get like 0.54. Okay, we get here a very small negative value. Also, okay, here is a little bit more, more negative, but still not -1. I don't see here anything close to -1, which we know is a true value. So this is systematically wrong, and this is also confirmed by this histogram. I put actually two measures, but let's speak first with the blue histogram, which is this, beta 1 estimates. We know that the true value is -1, so it is someone here, yeah? And it never happened in our 100,000 simulations to be even close to -1. What we are seeing here is actually, mean estimation is close to the +25, +0.25. We have only a small chance to have it negative. Yeah, mostly it's positive and closer to the 0.5 and then -1. So this is unfortunately something systematically biased. Yeah. And also we see here these p-values for the statistical significance. So maybe we would say, okay, if it provides such a wrong biased estimates, at least maybe it would be great to have those results not significant. But we see that here these p-values are quite so okay, in most cases they are not statistical significant, yeah, because we see that probably most p-values are above 10%. But this is not uniform, it's skew towards left-hand side, and therefore there are more than 10% cases that we would reject null hypothesis and stating that the impact is positive, impact of price on demand is positive, and moreover it's positive, yeah, which is in a wrong direction. So, but what we see is something which called bias. Bias is measured between the difference between the true value, which is -1, and the expected estimation, yeah, which is here plus 24. So plus 24 minus 1 is plus 1.24. This is a bias. So the magnitude error that we systematically make on our estimates. And you know, why is it the problem? The problem is also explained here that since the temperature is impacting both demand and price, and when we omit it here, its positive impact of temperature on demand, this relationship is somehow overtaken by the price. So price now have the information of both temperature with which it is correlated, and we know that temperature has positive impact, not negative as price itself on the demand. So it's like entering the shoes, it's more entering the shoes of the temperature and saying, hey, I'm like temperature and I'm impacting positively on the demand. So so this is the consequence of the omitted variable, yeah. And it might result in quite opposite direction of impact, yeah. And so, you know, takeaway would be here to try to control for more variables. Also, it's not, you know, fully good strategy to control for everything, because you will lose your degrees of freedom, and it is also not a good strategy. But you know, econometricians says you need to have theory, you need to have some model which you not always can get from data. So you need to assume something based on knowledge, expertise, and then you can help building such models. Yeah. So this is what I wanted to share with you today. And in the second, so we can easily start break right now. And the next part would be running by Łukasz. It will be about machine learning models, and it will start at 1 p.m. Till 3 p.m. So thank you very much. I'll be staying during the break. So if you have any questions, feel free to ask. Thank you very much.